What does linear mean in mathematics? It gets used in a lot of places. You have to distinguish between linear operators and linear equations. A linear operator, first, what's an operator? An operator is a verb, right? It's something that does something. It takes an input and gives you an output. They call them functions, mappings, transformations. That's what an operator is. It takes an input and it gives you an output. So what are the rules to be a linear operator? There's only two, and they're very simple. Rule one, if you multiply the input by a constant, the output gets multiplied by the same constant. Double the input, you double the output. The other is, if you add two things together and then put them as the input, you get the same result as if you put them in separately and then add the answer. That's it. Those are the only requirements. So what do linear operators do? Well, it depends what you feed it. If you feed a linear operator a number, it's going to give you out a constant multiple of the number. That's the only thing it can do. That's the only thing that's linear. If you feed it a vector, what you get out is a matrix times the vector. A linear operator on vectors is described by a matrix. Now, if you have a linear operator act on a function, now you've got a lot more options, because you can do various complicated things to functions to turn them into other functions and have it still be linear. You can take a derivative. You can take an integral. You could do both and add them up. You can multiply by a constant. So all sorts of things become possible so long as they satisfy these two rules. So that's what it means to be a linear operator. What about a linear equation? Linear equations include things like the classic y equals mx plus b. Now, we call that a linear equation because it's the equation of a line. If you graph it, you get a line. One problem is it's not quite a linear operator, right? This right-hand side is not linear because you can't do the plus b. Here's why. If y1 is mx1 plus b and y2 is mx2 plus b, when you add them together, you get mx1 plus x2 plus 2b. The b messes it up. If the b is 0, you're fine. So the right-hand side of this is not actually a linear operator. Next up, let's look at ax plus by plus cz equals d. This is actually the equation of a plane in 3 dimensions. The left side of it is a linear operator if you think of the input as being the vector x, y, z. It wouldn't be a linear operator if there was also a plus constant on the left. So the left side of this is a linear operator. Now, going further, we could have a set of equations, a system of linear equations. These equations are linear because you don't have any x squared or x cubed, which means it's possible to write it like this. You can have a matrix multiplying the vector xy to give another vector. And this is a linear transformation. We study these in linear algebra. One more detail about this. If you had a similar equation, y vector equals ax vector plus b vector, the right-hand side is no longer a linear transformation. It's obviously close. We just have plus a constant vector on there. But we know that that messes things up. But we still use these a lot. And so they gave them a slightly different name. They call them an affine transformation. So this right-hand side is an affine transformation, not a linear one. Now let's talk about linear differential equations. They come in two kinds, homogeneous and inhomogeneous, depending on whether the constant term effectively is 0 or a function of x. Constant in terms of not having any y's in it. Let's see an example. The capital letter D stands for the action take the derivative, the operator. So dy means y prime, d squared y means y double prime, etc. Let's take a specific linear operator, d plus 3, and let's prove that it's linear. First of all, what does that mean, d plus 3? It means when you act on y with the linear operator, d plus 3 acting on y means dy, which is y prime, plus 3y. That's what it means to have 3 act on y as an operator. It's multiplying it. Now let's prove that that is a linear operator. We've got to prove two properties. First, linear operator acting on cy means d plus 3 times cy. That's d cy plus 3 cy. Derivative is linear, so a constant comes out. So you can factor the constant out, and you get dy plus 3y, which is constant times the linear operator acting on y. So that's the first property. The second property is if you have L of y1 plus y2, then we're trying to act with d plus 3 on y1 plus y2. That gives us d acting on y1 plus y2 plus 3 acting on y1 plus y2. And then we can distribute dy1 plus dy2 plus 3y1 plus 3y2. Rearrange the order, dy1 plus 3y1, which is linear operator acting on y1, plus dy2 plus 3y2, which is linear operator acting on y2. So L of y1 plus y2 is L of y1 plus L of y2. And so d plus 3 is in fact a linear operator. Finally, some examples of nonlinear operators and linear operators. Nonlinear operators. The square root of y is not linear because it fails the constant multiple rule. Linear operator acting on cy is not c times square root y. You get square root c times square root y, which messes it up. Likewise, L of y equals y squared. The constant turns into a c squared instead of a c. Also, if you have y times y prime, right? Neither one of those is squared, but they are multiplied together, so you end up again with a c squared when you were supposed to get a c. This fourth example, L of y equals y prime plus 4. Now I want to carefully distinguish that from this kind of example. This is y prime plus 4. So if you do L of y1 plus y2, you get a single plus 4, but you were supposed to get a plus 4 for each of them. This is d plus 3 is y prime plus 3y, whereas that's just y prime plus 4, not 4y. That's the difference. This is a linear operator. So is this. So is derivative, of course. Now this one, x squared d squared plus 2xd. That is a linear operator because x is not the input. Y is the input. This is a linear operator acting on y. It is not linear in terms of x, but that's not what we're talking about. This is an operator acting on y. So in those terms, it is certainly linear. I hope that clears up some of the confusion about linear versus not linear. Thanks for watching.